Have you ever wondered how a sound engineer can take this absolute flood of music and just perfectly sculpt it for our ears? Well, it's not magic. It's actually a really brilliant piece of engineering. And today, we're going to pull back the curtain and uncover the secret behind how we can analyze and, more importantly, control any kind of signal. So, this right here, a graphic equalizer. This is the key to the whole mystery. You've definitely seen these things, right? These rows of sliders that seem to give engineers this, godlike control over the sound. But what are they actually controlling? Yeah, that's the real question, isn't it? When an engineer pushes up a slider to boost the bass, how does the machine even know what bass is? How does it separate that from, the singer's voice or the cymbals? The answer, it turns out, is hidden in the very nature of signals themselves. And this brings us to our first major clue. Turns out, even the most chaotic, crazy-looking signals have a surprisingly simple, almost elegant structure hidden deep inside. This is it. This is the secret, right here on this slide. Any signal, and I mean any signal, no matter how complex it looks, a guitar riff, a radio broadcast, you name it, can be broken down into a simple sum of pure, clean sine waves, each with its own specific frequency and volume. Okay, so let's actually see this in action. We'll build it up visually. Here in the top left, we've got one pure tone, just a single sine wave. This is our basic building block. It's clean, it's simple, totally predictable. Now, watch what happens when we add a second sine wave, one with a higher frequency. If you look at the top right graph, you can see the shape immediately gets more complex. It's starting to change. We're already building something completely new from these simple parts. And this is where it gets really mind-blowing. As we add a third and then a fourth sine wave, look what happens. We're actually building a square wave. Think about that. We've taken these smooth, curvy waves and combined them to create something with sharp, straight edges. This isn't just a math trick. This is fundamentally how signals are built. And this incredibly powerful idea has a name, the Fourier series. You can think of it as the mathematical recipe book that lets us take any complex signal and break it down into its simple sine wave ingredients. And of course, once you know the ingredients, you can start changing the recipe. So, we know that signals are made of sine waves. Great. But what kind of machine can actually take them apart and put them back together again? Well, that's where signal processors come into play. That machine is called a linear system. And for our purposes today, you can just think of it as a kind of black box. A signal goes in one side, the system follows a very specific set of rules, and a modified signal comes out the other side. Simple as that. And that abstract black box, it's not just some idea on a whiteboard. It's made of real-world stuff. Even a super simple circuit, like this one, with just a resistor and a capacitor, is a linear system that can change a signal passing through it. An equalizer is basically just a collection of more sophisticated versions of these little guys. Okay, so we have these systems, but every system is different. How can we possibly figure out the unique personality of any given system so we know exactly what it's going to do to our signal? We give it a personality test. We send in a standard, known signal, and then we just watch what comes out the other end. This is called the system's time response, and it tells us pretty much everything about its character. And this response usually has two parts. First, there's the transient response. You can think of this as the initial shock. The system kind of wobbles a bit as it adjusts to the new input. But that part fades away. What you're left with is the steady state response. That's the system's stable, predictable, long-term behavior. So the big question is, if we want to understand a system completely, what's the ultimate test signal? What's the one input we can use that will reveal everything about a system's inner workings, all in a single go? Well, the answer is a theoretical tool called the unit impulse. And I gotta say, this is a truly mind-bending concept. It's a perfect instantaneous kick, a signal that is infinitely powerful, but it only lasts for an infinitely short moment. Now, while it can't really exist in the real world, this one idea is the master key to understanding any linear system. This slide really helps visualize it. A real-world impulse, like tapping a microphone, has some width and height. But the theoretical unit impulse, it's just a perfect instantaneous spike right at time zero. It's the ultimate test because it essentially hits the system with every possible frequency all at the same time. And the result of this one test is, well, it's everything. As the source material says so perfectly, the way a system reacts to this one perfect impulse is its unique defining characterization. That response tells you absolutely everything you need to know. And here is what that looks like. We hit the system with that one perfect spike, and this graph shows how it responds over time. This is the impulse response. And it is the system's unique fingerprint. I mean it. No two different systems will ever have the same one. All right, now for the final piece of the puzzle. How does this fingerprint that exists in the world of time connect back to our equalizer, which we know works with frequencies? This is where it all comes together beautifully. That impulse response, the system's fingerprint, describes its behavior over time. But it has a mathematical twin called the transfer function, and that describes the exact same system, but in the language of frequency. They are two sides of the very same coin. And this graph of the transfer function, this brings us right back to our equalizer. It shows us exactly which frequencies the system lets pass through and which ones it blocks or weakens. This particular system is what we call a band pass filter. It favors a specific range of frequencies and tunes out the highs and the lows. Every single slider on that sound engineer's board controls a filter just like this. So there it is, the sound engineer's secret, totally revealed. Complex music goes into the equalizer. The machine understands that music as just a sum of simple sine waves. That signal then passes through a whole bank of filters, where each filter is designed to grab onto a specific range of frequencies. And those sliders, they simply control the volume of each of those frequency bands before everything gets mixed back together into the final sound we hear. But you know, this idea is so much bigger than just music. It's the absolute foundation of modern communications, of robotics, of control systems, so much more. And it leaves us with this one powerful final thought. If you know how a system responds to just one single perfect impulse, can you then predict its response to anything?